All right, guys, welcome back to our fourth lesson here in our AP review series. Today we're going to be looking at some derivative basics. And before we begin, I know I touched on this, I believe, in the last lesson, but I want to just mention it again. Notation for the first and second derivative. So if we're taking the derivative, or if you're asked to take the derivative, some different notation we might see, maybe y prime, dy dx, right? F prime of x, those are pretty common. Maybe you see something like this, the derivative of f of x with respect to x. Anything along these lines are talking about the first derivative. Whereas the second derivative, we might see y double prime, d squared y over dx squared, or maybe f double prime of x. And remember, the second derivative is just telling you to take the derivative of the derivative, and we'll probably get to that a little bit more later on. Okay, so let's walk through some basic rules today, and I'm not going to talk about derivative shortcuts at all in this lesson because that's something I feel like you probably already have down or could easily review on your own. So I want to focus today just on some of the main ways that we take derivatives. So let's begin with the product rule. And remember, the product rule is used when you have two functions multiplied together. So f of x times g of x. And when we take the derivative of two functions multiplied, we take each function, we multiply it by the derivative of the other function, and then we add those two together. Remember, the order that you do this in does not matter because it's addition. So as an example, or if you want to just pause the video and do this problem yourself, let's take the derivative of x squared sine x. So y prime would be equal to x squared times the derivative of sine, which is cosine, plus sine times the derivative of x squared, so that would be 2x sine x. You might have to simplify, factor out x, or things like that with the product rule, but I'm just going to leave my answer for this problem the way it is. Product rule is very simple. Just take your time and be careful with positives and negatives. That could be an area that's can be difficult. Okay, our second rule that we want to look at is the quotient rule. And remember, the quotient rule is used anytime you have two functions that are divided. So y is equal to f of x divided by g of x. The derivative, when you have two functions divided, you're going to take the bottom multiplied by the derivative of the top minus the top times the derivative of the bottom, and all over the bottom function squared. The other way that we remembered this in class, remember b to t minus t to b over b squared. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So as an example, and again, also if you'd like to try this one and do it on your own, let's say our function is y equals x squared plus 1 over the inverse tangent of x. I'm trying to hit a lot of the shortcuts here as we go through. So our derivative would be inverse tangent times 2x minus x squared plus 1 times 1 over x squared plus 1, and then all over the inverse tangent of x squared. And then hopefully everybody sees that we can simplify a little bit because the second part of this fraction is just equal to 1. And that's our derivative. That's a good example of the quotient rule in action. All right, moving on. Next up, we're going to have the chain rule. And if you remember, the chain rule is used when there is composition of functions. So if y is equal to f of g of x, y prime is equal to the derivative of f prime of g of x multiplied by g prime of x, the derivative of the inside. I want to do two problems with this one. So let's do example 1. Let's hit some good rules here. We got y equal to the natural log of x squared plus x minus e to the x. So when we take the derivative of this, we'll start with the outermost function, ln. The derivative of ln is 1 over x. So in this case, 1 over x squared plus x minus e to the x times. Now you go inside. Let's multiply by the derivative of the inside, which will be 2x plus 1 minus e to the x. I could move this to the top if I wanted to, or just leave it. This looks great to me. All right, example 2. Let's do one with a couple chains. 2 chains. Y equals sine squared 3x cubed. So when I take the derivative of this one, we're going to start on the very outermost function. That's raised to the second power, and sine is squared. So I'm going to begin with the power rule, moving that 2 to the front, and keeping everything else the same. And the new power is first power. Now, if we go inside, our next function will be sine of x, or sine of 3x cubed. So we take the derivative of sine, that's cosine. And then I finish it all off by taking the derivative of 3x cubed, which is 9x squared. So putting this all together, we have 18x squared sine of 3x cubed times cosine of 3x cubed. That's it. Very, very straightforward. Hopefully, as you're watching this, you're going, oh, it's so easy when I learned how to do this the first time. But it probably didn't feel that way when you were doing it. All right, let's move into some couple other ideas. I would be prepared. Just an extra note here. I would be ready to do these derivatives not just with functions, but with some generic functions, where maybe they give you different values. Like maybe you have a table that gives you f of x, f prime of x, g of x, and g prime of x, and you have to pull values from that table using the rules that we just did. That's why if you notice on each one, I wrote it in this notation first, like for the chain rule or for the quotient rule. So we could look at the general rule, not just with problems, but in a broader sense for situations that are a little bit different. Maybe it's a table that gives you these values. Maybe it's a graph that gives you these values. Something that makes you work with it in a little bit of a different way. And I think it's just something to be ready for, be prepared for as you work through this exam. Okay, last time we talked about tangent lines, and I want to talk a little bit more about tangent lines and normal lines. So if you remember, the derivative is the slope of the line tangent to a curve at a point. So it might look like this. And then also remember, a normal line is the line that is perpendicular to the tangent line at the point of tangency. So it might look like this. The slope of that normal line is the negative reciprocal of the tangent line. So it's pretty easy to work with. So let's look at a quick example. I want to write the tangent in normal to y equals inverse tangent of 2x at x equals 1/2. So I'd like to write both the tangent line and the normal line. So we're going to begin with the derivative. The derivative of the inverse tangent of 2x, that would be 1 over 2x squared plus 1 times 2, or 2 over 4x squared plus 1. Now we'll plug in our point. So at x equals 1/2, this will be 2 over 1 plus 1. So that is a slope of 1. That's my m tan. The m normal would be the opposite reciprocal. So -1 in this case. Okay. So if we go through from here, the other thing I need is the point. I know x is 1/2. So we need to know what is the y coordinate at that point. So I'm going to plug into the original and get inverse tangent of 1. And we know that that occurs at pi over 4 for tangent. And we're ready to write our line. So our line would be y minus pi over 4 is equal to x minus 1/2. That's the tangent. And then the normal line would be y minus pi over 4 equal to negative x minus 1/2. That's it. We can leave those just like they are. One application to be ready for with tangent lines is the linear approximation. So some problems might prompt you to use a tangent line to approximate a value of the function that's really close to 1/2. Like maybe I say, use this tangent line to approximate f of 1. You'd plug 1 in for x into your tangent line and then solve. So anytime you have to do a linearization, a linear approximation, a tangent line approximation, first get the tangent line and then substitute that value that you are trying to approximate at in for x. Okay, one last thing today. I'd like to look at implicit. I include implicit differentiation in sort of my basics because this should be pretty easy at this point. But let's say we have a problem. Let's say y cubed minus 2xy plus x squared is equal to 3. Let's say we need to take the derivative. What's dy dx for this problem? So just remember, we're taking the derivative in terms of x. So whenever we derive a y term, we're going to apply the chain rule and multiply by dy dx on the derivative of y. So that's the first part. We're going to use the product rule here for the middle. So minus 2x dy dx minus 2y plus 2x is equal to 0. From here, now my goal is to solve for dy dx. So any terms that don't have the dy dx, I'm going to send over to the right side of this equation. In terms with the dy dx, I'm going to keep right over here. So we're going to have 2y minus 2x on the right. And then we can easily factor out dy dx and divide. So we'll make that jump. I know you guys are all at this point. So 2y minus 2x over 3y squared minus 2x. And that's my first derivative for this problem, which could be used to find the slope. Maybe it's used to find horizontal tangents where the top is equal to 0, or vertical tangents where the bottom is equal to 0. Lots of different problems that we've seen already in our review that come from this. But maybe a problem says find the second derivative implicitly. Not a hard problem. We just have to do a little bit more work. So in this one, we're going to do the quotient rule with our implicit. So we're going to take the bottom, 3y squared minus 2x, multiply that times the derivative of the top, which would be 2 dy dx, still implicitly, minus 2. We'll subtract the top times the derivative of the bottom. So that's 6y dy dx minus 2. And then all over the bottom squared. Oh, now this is not in terms of x and y, and usually this problem would ask you to put this in terms of x and y. I'm not going to try to simplify it, but in order to do that, I would then now go and replace every dy dx with what dy dx is. This is not a nice problem that we have going on at all. But you get the idea here. Get my parentheses right, and that all over bottom squared. Okay, not going to try to simplify this, but maybe there's a value that you're solving it at or something to make it a little bit easier. Or maybe it's a lot simpler than this one, and it's a problem you can then simplify and work with. But, that's a good review of implicit. Remember, there's lots of problems you can do. Anything with derivatives can be done with now implicit problems, tangent lines, normal lines, vertical tangents, horizontal tangents, all that good stuff is now open for this. All right, that's it for today. I hope you guys enjoyed this video, and please let me know if you have any questions on anything as you are continuing to work this month. And happy studying.